An idea that's really captivated inventors, dreamers, and, well, let's be honest, even some fraudsters for centuries.
Yeah, this whole quest for limitless, clean, and crucially free energy.
Exactly. Think about it. The allure of perpetual motion, especially from something like a permanent magnet, which seems so persistent, right? It just
Right.
keeps pulling or pushing. It feels like it should work, you know?
It has a powerful intuitive appeal, absolutely.
So our mission today is a really rigorous look at the actual science. Can you really build a power-generating motor that runs just on static, permanent magnets?
Mhm.
We're going to dig into why this idea, compelling as it is, kind of slams right into the fundamental laws of physics.
Right. And look, for anyone hoping for that magnetic motor, the conclusion is pretty definitive. It's not about lack of trying or some suppressed secret tech. It's just,
Yeah.
well, it's unachievable because of these unyielding physical laws. We'll break it down using sort of three main arguments. The nature of the magnetic force itself, the big laws of thermodynamics, and mechanical stability, something called Earnshaw's theorem.
Okay, let's jump right into that core misconception then. People feel that magnet's force and think, why can't that drive something forever? What's the fundamental flaw there? How does a static magnetic field really work, or maybe not work as an energy source?
Well, the key thing, the fascinating thing, is that a permanent magnet's field is, by its very nature, a static property. It's
So,
not like a fuel tank you can drain.
so it's not like a battery slowly discharging energy. It's just part of what it is. How does it get that field in the first place?
Exactly. It starts super small at the quantum level with electron spin. In certain metals, iron, nickel, cobalt, these tiny magnetic bits line up in areas called domains.
Right.
To make a permanent magnet, you basically force those domains to align and you sort of lock them in place. That takes energy during manufacturing. Work has to be done on the material.
Okay. So the energy is put in up front.
Precisely. And that energy is then stored as potential energy in the magnet structure. It's kind of like a pillar holding up a roof. The pillar exerts a constant force, sure, but it doesn't do any work or consume any energy just by standing there.
Okay.
The proponents, they see that constant force, and they mistakenly equate it with constant energy generation. But a static field is like a loaded spring. It holds potential energy, but it doesn't continuously create more. That initial push or pull potential is all there is. No refill.
That's a really helpful picture, the pillar or the spring. So if the field is static, how does that connect to the basic rules about energy and doing work? You mentioned conservative force fields. What does that actually mean for magnets?
Oh, it means everything, really. Conservative forces, and this includes gravity, static electricity, and, importantly, the static magnetic force between permanent magnets. They have this defining property. The total work done by the force when you move something between 2 points. Well, doesn't matter what path you take.
Okay, unlike friction, say, where a longer path means more work lost.
Exactly. Friction is non-conservative. But for a conservative force, the inescapable consequence is that the total work done over any closed loop, like a motor's rotor spinning all the way around and coming back to where it started, is always zero.
Always zero.
Always zero. Think about designing that magnetic motor. For every bit of the rotation where the magnetic field pushes the rotor along, doing positive work, there has to be another part of the rotation where it pulls back or resists, doing an equal amount of negative work.
I see.
So the network you get out of that magnetic field over one complete continuous turn is, and physically must be, zero. The very thing that makes the magnet's field persistent, its static conservative nature, is exactly what stops it from being a net source of energy for rotation.
So if I'm visualizing this, it's like rolling a ball around a perfectly smooth, frictionless track that ends up back at the start height. You might go downhill for a bit, but you always have to go uphill an equal amount. Net gain, zero. Is that kind of the idea?
That's a great analogy.
Yeah.
Yeah. Proponents of these motors are essentially imagining they can build a track that's somehow downhill all the way around in a circle.
Which sounds impossible.
It is physically and mathematically impossible on this kind of potential energy landscape.
Hmm.
Any rotor, any moving part, is going to be pushed towards spots of minimum potential energy. Think of them as valleys of attraction or pushed away from peaks of repulsion.
Yeah.
It'll inevitably find a spot where the forces balance, an equilibrium point, and just settle there. That effect, where the rotor kind of clicks into place between magnets and gets stuck, that's often called magnetic cogging.
Okay, that zero network is a huge blow mechanically, But I guess these free energy ideas must also clash with the really big universal laws about energy itself. Are we talking thermodynamics?
Oh, absolutely.
Yeah.
This is where magnetic motors face a sort of double whammy and inescapable logical pincer from thermodynamics. First off, a self-powered magnetic motor producing usable energy would be what we call a perpetual motion machine of the first kind, a PMM1. The first law of thermodynamics, the law of conservation of energy states, flat out. Energy cannot be created or destroyed, period.
Right. Can't make something from nothing.
Exactly. A PMM1 claims to do work without any energy input, creating energy ex nihilo out of thin air. Since we've established the static magnetic field provides zero net energy input over a cycle, any work the motor did would have to be created from nothing. Impossible. Forbidden by the first law.
Okay, strike one. What's the second part of the pincer?
That's the second law of thermodynamics.
Hmm.
This introduces the concept of entropy, which is basically a measure of disorder or randomness in a system. The second law says that in any real process in an isolated system, the total entropy must always increase, or at best, stay the same in some ideal theoretical cases.
Meaning things tend to run down, become less organized.
In a way, yes. It means a perpetual motion machine of the second kind, a PMM2, is also impossible. That would be a machine that could, say, take heat from the surroundings and convert it all into useful work with 100% efficiency, essentially reversing the natural tendency towards disorder.
And how does that apply to our magnetic motor?
Well, more directly, for any real machine, you always have non-conservative, dissipative forces. Think friction in the bearings, air resistance slowing things down.
Right, real world stuff.
These forces inevitably convert useful, ordered mechanical energy into disordered thermal energy, basically. Waste heat. That heat just dissipates and isn't available to do more work. So without some continuous external energy source to make up for these losses, any real machine that starts moving must inevitably slow down and stop.
So let me see if I've got this. The first law says you can't win, you can't get more energy out than you put in. And the second law says you can't even break even in the real world because of friction and losses.
That's a perfect summary. First law. Output can't exceed input. Second law. In reality, output will always be less than input because some energy is always lost as heat.
So for a magnetic motor, where the claimed input from the magnets is effectively zero over a cycle.
The first law says the maximum possible output is zero. And the second law then confirms the actual output must be negative. It will just use up whatever initial push you give it to fight friction and then grind to a halt. No way around it.
That seems airtight. A pretty solid case from physics. But okay, what about the practical side? The actual building of these things, the arrangement of the magnets, the geometry, does that throw up its own roadblocks?
It absolutely does. And this brings us to a really elegant piece of physics called Earnshaw's theorem from way back in 1842. It's probably the most definitive statement specifically about the stability of static field arrangements.
Earnshaw's theorem. Oh, okay, what does it say?
It proves, mathematically, that you cannot hold a collection of charges or, crucially for us, permanent magnets in a stable, stationary equilibrium, using only their static electric or magnetic forces.
Stable equilibrium. What does that mean practically? Like keeping the rotor perfectly balanced and spinning?
Sort of. Think about stable equilibrium like a marble resting at the bottom of a bowl. If you nudge it, it rolls back to the bottom. That's stable. Earnshaw proved that static fields, like those from permanent magnets, can't create a true bottom of the bowl in free space. They can only create saddle points.
Saddle points, like a saddle on a horse.
Exactly like that.
Mm-hmm.
Imagine trying to balance a marble perfectly on the middle of a saddle. It might be stable if you push it forwards or backwards along the horse's spine, it'll roll back. But if you push it sideways, it falls off. Stable in some directions, unstable in others.
Okay, I can picture that. So static magnet fields only create those saddle points, not true stable points.
Correct. And the implication for a magnetic motor is profound and, frankly, fatal. It means no static arrangement of magnets can give you a stable push in one direction, like making it spin, without also creating an instability or an even stronger pole trying to trap it somewhere else.
Mm-hmm.
The rotor will always find one of these equilibrium points. Maybe a saddle point, maybe a minimum along one axis where the force is balanced, and it will just stop there. It can't be stably pushed around continuously.
Mm-hmm.
Earnshaw's theorem is really just another way of expressing the consequences of the magnetic field being conservative, but looking at it from a mechanical stability viewpoint.
Wow. So the physics is saying no from multiple angles. Energy conservation, entropy, and now mechanical stability too. It just seems like it can't work. Yet you go online and the internet is just flooded with videos, diagrams, tutorials claiming, here it is, a working magnetic motor. what stands out to you about the history here and these persistent online claims?
Yeah, that persistence is remarkable, isn't it? It speaks to how appealing the core idea is. Historically, you see figures like Mike Brady and his Perendev motor.
I think I've heard of that one.
It used angled magnets with the claim that this specific geometry created a continuous net rotational force. But again, it's a geometric illusion. The underlying magnetic field is still conservative, so the network over rotation has to be zero. Despite flashy videos online, no independent group could ever replicate it and get net energy out. And, well, Brady himself was eventually convicted of fraud related to investments in it back in 2010.
Okay, so that one ended badly. What about others? I sometimes see patents mentioned as proof.
Oh, yes. Howard Johnson's patent from 1979 is a common one cited by free energy enthusiasts. U.S. patent 4,151,431. But here's the crucial thing people often miss. A patent is a legal document granting rights. It is not a scientific validation or proof that something works.
The patent office doesn't, like, build it and test it.
No, especially not if the claims seem to violate fundamental physics. They primarily check for novelty and clarity. Johnson's patent uses a lot of non-standard, arguably pseudoscientific language. And it fundamentally ignores both the conservative nature of magnetism and Earnshaw's theorem. Predictably, attempts by others to actually build a working device based on it have consistently failed.
So the science is stacked against it, the historical examples are dubious, but still, you see these YouTube videos. A guy in his garage, magnets spinning. What's usually going on there?
Right, those online designs. They almost invariably rely on a few common tricks. Sometimes there's a hidden power source, a small battery driving a tiny, quiet motor cleverly concealed.
Shaky.
Or they use external forces. Maybe an off-camera fan providing a gentle push, or the whole setup is on a very slight, almost imperceptible slope. Gravity does the work, not the magnets. And then there's just misleading presentation. They'll give the rotor a really strong initial push, film it while it's spinning down, and then cut the video before friction inevitably brings it to a complete stop. It looks impressive for a few seconds.
Classic misdirection.
It really is. The absolute key giveaway, the hallmark of pseudoscience versus real science, is the complete lack of independent critical replication. If these designs worked, labs and universities worldwide would have replicated them. They haven't. The persistent failure isn't because of some vast conspiracy suppressing free energy. It's because these devices simply cannot work according to the fundamental unchangeable laws of physics.
Okay, that makes sense. So if static magnets are a dead end for generating free energy, how do magnetism and electricity actually work together in the real world to give us power? How do we legitimately harness them for, keeping the lights on?
Now that's a crucial distinction, and where magnetism becomes incredibly important. It's central to almost all large-scale power generation, but the key isn't a static magnetic field, it's a changing one.
Changing. How so?
This is governed by Faraday's law of induction, discovered by the brilliant Michael Faraday back in 1831. He found that if you change the magnetic flux, basically, the amount of magnetic field passing through a loop of wire, you induce a voltage, an electromotive force, in that wire.
And that voltage can drive a current.
Exactly. And you can change that flux in a couple of ways. You can move a magnet near a coil of wire or move the coil near the magnet. Or, most commonly in generators, you rotate either the magnet or the coil relative to the other.
So those huge turbines you see at power plants, wind turbines, hydro dams, steam turbines, they're all essentially just spinning magnets near coils or coils near magnets.
Fundamentally, yes. That rotation, driven by an external mechanical energy source, wind, water, steam pressure, causes a continuous change in the magnetic flux through the generator's coils. This induces a continuous alternating voltage and current. That's our electrical power.
But wait, that external energy source is key, right? You still need the wind or the steam. It's not free.
Absolutely not free. And there's another crucial piece, Lenz's law. It states that the induced current creates its own magnetic field, and this new field opposes the very change in flux that created it in the first place.
Opposes it? What does that feel like?
It feels like resistance. It manifests as a magnetic drag, or torque, that actively resists the rotation of the generator. To keep the generator spinning and producing electricity, the external power source the turbine has to continuously work against this magnetic drag.
Oh, okay.
The mechanical energy the turbine supplies to overcome this resistance is precisely what gets converted into electrical energy. It's a transformation of energy, not a creation. There's still no free lunch. Energy in equals energy out, minus inevitable losses. And this highlights the critical difference between an electric motor and an electric generator. A motor takes electrical energy in and converts it to mechanical energy out, rotation. A generator does the opposite. It takes mechanical energy in, rotation from a turbine, and converts it to electrical energy out. A single device can't be both its own motor and its own generator with a net positive energy output. That idea, sometimes called bootstrapping, where a motor drives a generator which then powers the motor, that's just another PMM1 in disguise. Because of all the energy losses, friction, heat in the wires, the generator will always produce less energy than the motor needs to run itself. The system winds down very quickly.
Okay, so the physics is clear. No free ride from static magnets. But if we understand these laws so well, how do engineers actually use that knowledge, not to break the laws, but to work with them to make things better, more efficient?
That's where the real innovation happens. It's all about intelligently managing and conserving energy by working within the laws of physics. A great example is magnetic bearings.
Magnetic bearings, how do they work?
Well, in almost any machine with rotating parts, traditional mechanical bearings like ball bearings are a major source of friction. Friction wastes energy, turns useful mechanical motion into useless heat.
Right. Things get hot, wear out.
Exactly. Magnetic bearings use electromagnets, carefully controlled, to levitate the rotating shaft. So the shaft floats on a magnetic field with no physical contact.
Wow, so virtually no friction.
Precisely. This allows machines, like high-speed turbines or flywheels for energy storage, to operate much more efficiently, with drastically reduced energy losses due to friction. But critically, they don't create energy. They just significantly cut down on waste. In fact, active magnetic bearings need a continuous small input of electrical power for their control systems to maintain stability.
So they use a little energy to save a lot more.
Exactly. They're a perfect example of using physics and electromagnetism in this case to mitigate the losses predicted by the second law, not trying to ignore them.
That's clever. Are there other examples like that?
Oh, yes. Regenerative braking is another fantastic one, especially relevant now with electric and hybrid cars.
Right. My EV instead, how does it actually work?
Okay, so in a normal car with friction brakes, when you hit the pedal, brake pads clamp down on discs, and the car's kinetic energy, its energy of motion, gets converted directly into heat through friction. That energy is just wasted, dissipated into the air.
Gone forever.
Yep. Regenerative braking, though, tries to recycle some of that kinetic energy. When you lift off the accelerator or gently brake in an EV or hybrid, the electric motor that normally drives the wheels temporarily switches its function. It becomes a generator.
Ah, like we discussed before.
Exactly. The wheel's momentum now turns the motor generator, and instead of consuming electricity, it produces it. This generated electricity is sent back to recharge the battery pack.
So you recover some energy you'd otherwise just lose as heat.
Correct. The magnetic drag created during this generation process is what actually slows the car down. That's the braking effect. It's an energy recovery system, not energy creation. It makes the vehicle more efficient overall by recapturing energy that would otherwise be wasted.
These both sound like really smart ways to engineer within the rules, not fight them, using the physics to our advantage.
That's precisely it. True engineering progress, especially in energy, comes from understanding these fundamental laws deeply and using that understanding to design more efficient systems, to manage energy flows intelligently, to conserve energy and reduce waste, not from chasing the impossible dream of creating energy from nothing.
So, wrapping this all up then, what's the big takeaway for us listening? Why was this deep dive into magnetic motors so important?
Well, I think it boils down to this.
Yeah.
The idea of a self-powering motor running only on permanent magnets, while really captivating, is unfortunately a scientific dead end. And our conclusion today that it's impossible, it rests on really solid ground. We've seen three independent but converging lines of reasoning from physics.
Right, the three pillars.
Exactly. First, the conservative force argument. Static magnetic fields are conservative, meaning the network done over a closed loop like one rotation is always zero. You can't extract continuous energy. Second, the thermodynamic argument. These devices would have to violate both the first law of thermodynamics, creating energy from nothing, a PMM1, and the second law, by ignoring the inevitable energy losses due to friction and heat, essentially pretending to be a PMM2 or better.
Can't be done.
Can't be done. And third, the stability argument. Based on Earnshaw's theorem, static magnets simply cannot create a configuration that provides stable, continuous propulsion. Any arrangement will inevitably lead to the rotor settling into an equilibrium point and stopping.
So, multiple fundamental laws all pointing to the same conclusion. it won't work.
Unequivocally, yes.
Which really leads to a final thought, doesn't it? The genuine search for new, sustainable energy solutions, which is incredibly important, has to be guided by these proven, established principles of physics. Not by chasing this persistent, but ultimately impossible, dream of perpetual motion from magnets. Real progress, real breakthroughs will come from mastering the laws of nature as they are, not from trying to find loopholes that just aren't there.
Well said. Understanding the rules lets you play the game effectively. Trying to cheat physics just doesn't work.
Thank you so much for joining us on this deep dive today. Really fascinating stuff. We'll see you next time.